In this video, we're going to talk about solving a linear system of equations, which when I write it in matrix form, looks like a times x equals b, using what's called parametric vector form. So a lot of the examples that I'm going to do in this video are going to be a review because it's going to involve setting up an augmented matrix and row reducing it. Just at the end, we're going to write our answer in a more condensed format, which is parametric vector form. Okay, so I want to begin with a definition. So when we look at the equation a times x equals the zero vector, this is what's called the homogeneous linear system. Okay, so if we expand out the left-hand side of this, so a times the vector x. So remember, from the last section, doing that, we get a linear combination of the columns of A. So where the weights are the entries of x. So x1, x2, up until xn. So if I look at this equation and I wonder, well, when is this linear combination going to be equal to 0? There's one thing that always works, which is if x1 and x2 and all of those x's equal 0. So that is always a solution to this system of equations. And it's so simple because if we just set all the variables equal to 0, this is called the trivial solution. Okay, so what I want to do next is I want to do an example where we solve a homogeneous linear system. Okay, so here is the example. Let's find the solution set of the following system, and we'll write it in what's called the parametric vector form. Okay, so I have these 3 equations and 5 variables, x1 up until x5. Okay, so to find the solution set, we begin by writing this in matrix form. So I went ahead and wrote the augmented matrix for this. So that's this matrix that I have here on the left. I've also gone ahead and row reduced it. So that's the matrix here on the right. So these numbers hopefully look a little bit familiar. And that's because we actually row reduced the coefficient matrix. The coefficient matrix is everything that's on the left-hand side of the augmented bar back in section 1.2. All I've done is I've actually just taken that example from 1.2 and just changed the numbers that I have on the right side of the equal signs to zeros. Okay. But when I do row operations with just a bunch of zeros in this column, all of those numbers stay as zeros. So that's why even after I row reduced it, I have zeros on the right-hand side. Okay, so this is in reduced echelon form, this matrix over here. So this is in RREF form. Once we have that, if I want to write down my solution, we are ready to write the equation down for each row. So for the first row, the equation is x1 minus x2. There's no x3 term, so I'll leave a space for that, minus 5x4. There's no x5 term, and then that equals 0. The next second equation would be there's an x3, 1x3, plus 4x4 equals 0. And then the last equation, maybe let me leave a little bit of space for what the x5 would be. The last equation is just 1x5 equals 0. Okay, so we write down the equation for each row. So the next thing I want to do is I want to identify what my pivot variables are. So looking at my reduced row echelon form, here's the pivot in the first row. This 1 is the pivot in the second row, and then this 1 is the pivot in the third row. So what we do next is we want to get the pivot variables in terms of the free variables. So in other words, I want to isolate the pivot variables. So there were pivots in columns 1, 3, and 5. So that means x1, x3, and x5 are the pivot variables. Let's isolate them. So isolating x1, I get x1 equals x2 plus 5x4. x3 equals negative 4x4. And then isolating the x5, well, that's kind of nice. x5 just equals 0. Okay, I've deliberately left a little bit of space in between x1 and x3 and x5 so I can say what x2 and x4 are. So x2 and x4 are both free. So I'll just indicate that they're free. So they are both free. So back in the first couple of sections, when we wrote down the solution to linear systems, we left our answer like this. Now that we have the machinery of vectors, let's write down our answer, our general solution, in vector form. The general solution. Okay, so let me call it the vector x. So x has entries x1, x2, x3, x4, and x5. And for each of these entries, let's plug in what they are. So I know up here that x1 equals x2 plus 5x4. Okay, so plugging that in for the first entry, I get x2 plus 5x4. Anything that's free, like x2 is, I leave it alone. So x2, I leave it alone because it's free. x3, I have my equation. It equals negative 4x4. And then x4 is free, so I leave that alone. x5, well, x5 equals 0. Okay, so we've got our answers looking like this. The next thing that I do is I split up this vector into a sum of vectors based off of how many free variables appear in this. So I see two free variables. So I see an x2 and I see an x4. So what I'm going to do is I'm going to sort of generate a vector that contains all of the x2 terms. And I'm going to factor the x2 out of all of those terms. And then I'll also have a vector that has all the x4 terms in it. And I'll factor the x4 out. Okay, so I'm going to write my answer in this format. So I see an x2, for example, in the first entry. I see one here, and I see it in the second entry. So after I factor an x2 out of those two terms, I would be left with a 1 and a 1. None of the other entries have an x2. So what I would be left with is zeros in each of those spots. Okay, just as a quick check, if I were to distribute the x2 back into each of these terms, if I were to distribute x2 in, and in, and in, and so on, it's going to give me the terms that I'm seeing here. Like the first two entries would end up being this x2, and then this x2, and then I just get zeros for the bottom three entries. Okay, so let me erase those. Okay, so next let's do the same thing with the x4 terms. So I see the coefficient of x4 in the top is 5. In the second entry, there's no x4 term, so its coefficient is 0. In the third entry, the coefficient of x4 is negative 4. In the fourth entry, it's a 1. The fifth entry doesn't have any x4, so the coefficient is 0. Okay, and this is our general solution in what's called parametric vector form. So parametric vector form. Parametric vector form basically means, write your general solution as a vector, splitting it up into like its components based off of the free variables that we see. Okay, let's do another example. Okay, so we talked about homogeneous linear systems. So we can similarly define a non-homogeneous linear system, which is if we have an equation of the form a times x equals b, where b is not the zero vector. So let's do an example of one of those to see what does the solution set look like. Is it different? How is it different? Okay, so here's the example. I got the exact same setup on the left-hand side of my equal signs. I've just changed the numbers on the right-hand side to 1, a 7, and a 1. So we'll begin in the same way. We'll set up our augmented matrix, and we'll row reduce it. And this augmented matrix is actually the exact same as one of our examples in section 1.2. And we row reduce that to RREF form. So this matrix that I have on the right should be the same as what we've seen in an earlier example in a previous video. Okay, so from here, I'm good to write down my equations. So let's write down our equations based off of what we see on the right-hand side. Okay, so I know that the numbers on the right-hand side of the equal sign should change. I'll have a negative 9, I'll have a 4, and I'll have a 3. And then just like before, I want to isolate the pivot variables. So I want to isolate x1 because the first column has a pivot. So x1 equals, well, there's that 9, plus x2 plus 5x4. X2 is free. So x2 is free. x3, so we'll isolate that in the second equation. x3 is equal to, the 4 is there, and then I'll have minus 4x4. x4 is free. And then x5, we know what that is based off of the third equation. x5 equals 3. Okay, so we got our equations. Now we're ready to write our answer in vector form. So x as a vector has entries x1, x2, x3, x4, and x5. So actually I drew this vector a little bit bigger than I needed to. Let's shrink that. Okay, and then let's plug in what each of these is. So x1 is 9 plus x2 plus 5x4. x2 is free, so anything that's free, we leave it how it is. x3 is 4 minus 4x4. x4 is free, so we leave that how it is. And then x5 equals 3. So I'm just keeping the numbers in blue that are different from the last example to sort of highlight how this solution is going to be different. So for the most part, it looks the same, except for the 9, the 4, and the 3. Those numbers are different. And I think I'm realizing that I made one sign error. So this -9 didn't move to the other side. Sorry, if you guys caught that, awesome. That, I believe, should be a -9. The other numbers were good, the 4 and the 3. Okay, so what I want to do next is I want to put this in parametric vector form. So just like before, I will have a vector with all of the coefficients of x2 in it. We will have a vector with all the coefficients of x4 in it, because those free variables are appearing. But we will also have a vector with all of the extra constant terms that weren't associated with any of those variables. So those constant terms are -9. There's none in the second entry. Then there's a 4. There's nothing in the fourth entry. And then there's a 3. So what are the coefficients of x2? This should be the same as the last example. It's 1, 1, 0, 0, 0. Because the last 3 entries didn't have any x2 terms over here. So finally, the coefficients of x4 are 5, 0, -4, 1, and 0. Okay, so this is our general solution right here. Our general solution in parametric vector form looks like this. So one key thing I want to observe about this is, whenever we solve this non-homogeneous system, if it has an answer, the part with free variables in it is always going to be the same as what it was for the homogeneous case. So I'm going to call this portion VH, this vector. This is the homogeneous solution. That is always going to appear in the solution to AX equals B if it is consistent. And then there will be this extra vector here that's added to that. I'm going to call this VP, and VP stands for what's called the particular solution, and I'll explain what that is right now with the definition, actually by stating a theorem. So I'm going to state generally what happens when we solve the equation AX equals B. So if we look at that equation and B is not equal to 0 vector, the solution looks like, if I call it X, X is going to be equal to VP plus VH, where VP is what I call the particular solution. So what a particular solution is, it's exactly one solution. It's one specific solution to the equation AX equals B. So that means if I plug in VP in for the X, it satisfies that equation. So A times VP equals the vector B. So that's what VP is. It's one particular solution to the equation A times X equals B. And VH is the general solution of the homogeneous equation, A times X equals 0. All right. So I want to end this video by talking about what do these two types of solutions look like graphically. How do they compare to one another? Okay, so in the example we just did, all of our vectors were in R5, which we can't visualize. We can't visualize 5 dimensions. So I'm going to just draw a picture in R3. So let's imagine we have our x-axis, our y-axis, and our z-axis. And first what I'm going to do is, let's graphically draw the solution to a homogeneous system of equations. So if we have a times x equals 0, the solution is always going to go through, this goes through the origin. Since, and the reason why is because if I plug in the 0 vector, which corresponds to the origin, that is a solution to the equation a times x equals 0. If I plug in the 0 vector for the x, this works. It satisfies it. So that means the 0 vector, so if I just draw that, that's just a dot at the origin. The solution set should go through that dot. It should go through that origin. So graphically, that could look like a bunch of things, but I'm just going to, for the sake of this example, draw a plane. So maybe my solution set is this plane right here. So let's say that is the solution set. It doesn't have to be a plane. I'm just drawing it to visualize it. So when we talk about the solution to the non-homogeneous equation, what I'm going to do first is I'm going to draw the vector VP. So I'll just draw that. Let's put it in a different color. So VP is going to be some vector. Let me just draw it this way. So when we draw the solution to the equation ax equals b, graphically, this is parallel to the solution to the homogeneous equation, to ax equals 0, and it goes through VP. In other words, what that means is if I go up to the example that we just did, because the solution contains VH within it, it should look really similar. So in my picture, I'm drawing a plane for VH. And then what this VP is going to do is it's going to shift that picture a little bit. So it's going to shift my plane. It's going to shift it in the direction of this green vector. So I'll draw my plane, sort of emanating from there, just so I can see it. And that is what the solution to ax equals b looks like. So the solution to the homogeneous system and to the non-homogeneous system, they're parallel to each other. It's just the non-homogeneous system has been shifted in the direction of VP.